In this video, we're going to be talking about uses of the second derivative. Concavity, points of inflection, we'll do the second derivative test, maybe a little more particle motion, things like speeding up and slowing down, stuff like that. All right, so we'll start with our definitions of concave up and concave down. Okay, we say that the graph of f is concave up if f prime is increasing. Okay, now I'm going to draw a picture of that happening. So I'm going to draw a picture, okay, I'm going to concave up. I'm going to draw a picture of what that looks like in terms of f. Okay, well, say we're starting out with a positive slope, but the slope is increasing. Really what we're seeing is this second derivative is somehow dealing with the curvature of the function, right? Or maybe it's decreasing. So the slope is negative, but it's increasing, getting closer to 0. Okay? And what I would say about this curve is that it's smiling. Okay. We just said that f prime is increasing. What could you say about the second derivative if you knew that the first derivative was increasing? It's positive, right? Because if something is increasing, that means its derivative is positive. So if f prime is increasing, that means the derivative of f prime is positive. So that means f double prime is positive. Yeah, the relationship between f and its first two derivatives, the increasing, decreasing, concave up, concave down, that will all become second nature with a bunch of practice. Okay, let's take concave down. Okay, you might be expecting, I'm going to say f is concave down if f prime is decreasing. Okay, so we can, go over here and draw some pictures and let's say concave down. Okay, well, let's start if, maybe the slope was starting positive, but the slope was decreasing. Okay, it's like that. Okay, or maybe, the slope was negative, but decreasing, so getting more negative. Okay, and I might say that this graph is frowning. Something like that, Okay. We said in the definition that if it's concave down, that's because f prime is decreasing. Okay, so what could you say about the second derivative at a place where the graph of f is concave down? 0.005. Negative, yes. There you go. So let's do a couple of examples like we did last time. Let's look at a function algebraically. Let's look at a graph. Let's do some stuff. All right. Here's a function, and it's going to ask you to determine where f is concave up and concave down. This is exactly like the question we did last time where it said determine where the function is increasing or decreasing. Right? Just exactly the same. So 0970, you're a veteran of calculus AB. When you saw concave up or concave down, what was the first thing you were thinking? Yeah, no, but if you're asked to find where it was, what are you going to take? Yeah, take the derivative twice, get that second derivative. Yes, you said it over there, 799. Take the second derivative. So that's the first order of business. Okay, y'all, in class, I'm going to freeze the screen. But if you're watching at home, you can just follow along with me taking the first two derivatives. Okay, so y'all take the first two derivatives using the power rule, and then we'll check back in. Oops, made a little error there. Oh, that's... Okay, if you've already got your second derivative, you might want to factor the thing. Because, right, we're going to need to determine where it's positive or negative. So the best way to do that is to find the zeros, sketch a graph, make a sign chart, something like that. But regardless, you need the zeros. Okay, so there it is. Okay, I took the first two derivatives, and I got x to the third minus x. Okay, but in order to really sketch the graph of this thing, I'm going to need to factor it. Or if I want to make a sign chart, I need to find its zeros. Okay, so that's x, x plus 1, x minus 1. Right? Well, this thing that I'm, highlighting here in blue is a third-degree polynomial with positive leading coefficient. So, in some sense, it's going to, kind of come up, decrease, and then increase again. And since all three of its roots are single roots, we know it's going to, pass through confidently at each place. Now, of course, we'll have one with a double root and a little bit, but this is what we're looking at here. All right, now, this is what we're looking at here is the graph of f double prime. Okay, so if we're thinking about concave up, we're interested in where f double prime is positive. So I'm going to say f double prime is greater than 0. I'm going to kind of color in over here where f double prime is greater than 0. And that's looking like, the interval from -1 up to 0. You could write this as an inequality if you liked. And also over here, 1 to infinity. And so 1 to infinity. You could say -1 is less than x is less than 0, or x is greater than 1 if you want it. It would be exactly the same. If I wanted to talk about concave down, okay, well, that's where f double prime is going to be negative. So I'm over here, I'm coloring where it's negative. That's where it's negative. That's x is less than -1, or maybe also x is between 0. Okay, so see, I'm doing the interval for one of them and the inequality for the other. It's probably not the best form, but what I'm trying to tell you is that either one works for me, or for anybody, right? Because they mean the same thing. Next, here we have the graph of the derivative given, and the question is going to be, where is f concave up and concave down? Well, if we go back to our original little table that we made when we were defining concave up and concave down, in terms of f prime, concave up is where f prime is increasing, and concave down is where f prime is decreasing. So let's go back to the graph. And now our job is to determine where is f prime increasing or decreasing. Okay, so concave up, that's going to be where f prime is increasing. Okay, so that's kind of through here, yes, all the way up. Yes, there we go. And then also over here too. All right, so that is x is less than -1. Or potentially x is greater than +2, right? And concave down is going to be where f prime is decreasing. All right, and that looks to be between -1 and +2. Now, again, you could write that as an interval. Maybe I'll do that. Right? You could even make that a closed interval if you want. Nobody's going to object. It depends on your definition of increasing, really. Is something increasing where it's greater than or equal to 0, or is it just strict? What do you think? I don't know. All right. Now let's talk about points of inflection. Okay. The graph of f of x has a point of inflection at an x value where there is a change in concavity. That is, where we switch from concave up to concave down, or concave down to concave up. So again, let's kind of go over here and make ourselves a little table. All right, in terms of f's derivative, and f's second derivative. All right, well, there's, kind of a couple of forms that this could take. If f was smiling, but then it started frowning, right, that would be a point of inflection. If f was frowning, but then, it had an attitude adjustment, and then it started smiling, that would also be a point of inflection. Okay, notice how that kind of looks like, when there's a triple root in a polynomial and it kind of like slides through. That is always going to happen at a point of inflection. You could take the derivative twice using, probably the product rule if it was factored already, and you could show that there's going to be a change in concavity at a place where there's a triple or quintuple or seventh order root. Okay, something like that, a change in concavity. Well, in f prime, I know that concave up is f prime is increasing. And concave down is where f prime is decreasing. Or, concave down, f prime decreasing, to concave up, f prime increasing. So this is going to be at a direction change in f prime. Okay. What about f double prime? What's going to be changing when we change concavity for f double prime? Yeah, it's going to cross the x-axis. There's going to be a sign change. There's a bunch of different ways to say that. Okay, so I'll call it, I think, a sign change. All right, and so that's going to be looking something like, we had it going from negative to positive, maybe it going from positive to negative, or potentially, maybe, like a jump discontinuity. Yes, that is a sign change. It went from negative to positive there. Okay. Now, we'll talk more about that case in a moment. Now, what can we say about f? I've got a direction change, a sign change. Maybe I'll call it a attitude change. Okay, so I'm going to start you off pretty easy. I'm just going to ask you, how many points of inflection does the graph of f have? Not like, where are the points of inflection? Just how many are there? Okay, so point of inflection, due to its being, a change in concavity, we're going to need to take the second derivative. And I want y'all to resist the temptation to just take the second derivative, set it equal to 0, and solve. Because you're going to want to do that. And the thing is that there are points of inflection where the second derivative is not 0, because it's undefined. And there are places where the second derivative is 0 that are not points of inflection. So I'm not going to say they don't have anything to do with each other, but you've got to verify the sign change, right, in the second derivative. So what we're going to do is we're going to take two derivatives. Okay, so maybe y'all do that. If you're at home, you should pause the video because I'm going to pause it right now. All right, there you go. There's your second derivative. Okay, 4x squared minus 2x to the third. Now, if we're going to sketch a graph of this thing, we're going to want to factor this. So I'm going to factor out an x squared and, I suppose, a 2 as well. And then I'll be left with a 2 minus x. All right. Now, f double prime is a third-degree polynomial with a negative leading coefficient, which means that it's going to kind of come from above and then eventually go down, right? It has zeros at x equals 0 and x equals 2. And at x equals 0, it's going to bounce. And if you prefer to make a sign chart, you go ahead and do that. I like to sketch the graphs. So I'm going to go over here. I'm going to say this thing is bouncing. And then at x equals 2, it is passing through confidently. Okay. So the question is, and I'm going to remember to label my graph. It's the second derivative of f. how many points of inflection does the graph of f have? 1. Well, I'm seeing 2 zeros. What's the deal with x equals 0? Yeah, there's no sign change because of the multiplicity 2. And if there's not a sign change in the second derivative, it isn't going to be a point of inflection on the graph of the original. So I've got myself a point of inflection right there, and I'm going to say 1 sign change in f double prime. That means 1 point of inflection. Right? So the first example, I am illustrating you where we can have the second derivative equaling 0, but it is not a point of inflection. Right? All right. Now, this is an example that it's good for us to go over because it's kind of like the opposite of the last one. It's going to be a point of inflection where the second derivative is not 0. But the first year I taught Cal BC, which was in 2015, 2016, they went and took the AP exam, and they came out, and they were all asking me about if it's a sharp corner in the graph of f prime, is there a point of inflection in the graph of the original? And it's like, oh, man, I definitely didn't prepare them for that. Didn't even think to go over that type of situation. I just didn't know very much at that time, like what's on the AP exam, stuff like that. Okay. So the question here is, it's related. The graph of G prime is shown. Is the point I've labeled, x equals 3, an inflection point on the graph of the original, on the graph of y equals g of x? Okay. Well, I'm going to tell you it's yes, and I'm going to explain why. Okay. Over here to the left of 3, G prime is doing what? What is the graph doing? Okay, G prime increasing. That means G is concave what? Yes, up. Okay, then afterwards, G prime is decreasing, meaning the graph of G is concave down. Meaning that at 3, there was a change in concavity. It went from concave up to concave down. A change in concavity is a point of inflection. Okay, so despite the fact that the second derivative is clearly undefined due to the sharp corner, there is still a point of inflection in the graph of the original. You might be thinking, wouldn't this maybe cause a discontinuity in the graph of the original? It's a valid question, right? But if we look real closely, right there, we see that G prime of 3 is defined. It's some positive number. So that means that G is differentiable at 3. And we know that that means G is continuous at 3. So there's no second derivative. Yes, that's true. Okay, so there's something weird happening in the graph of G, but it's continuous and it's differentiable. If we could draw the graph of G, which we don't know how to do yet. Maybe eventually we will. Okay, now we're going to talk about the second derivative test. Okay. And what we're going to do is we're just going to draw pictures and then draw our conclusions. Okay. If f prime is equal to 0, what does that mean? What's happening with the graph of f if f prime is 0? Horizontal, yes. Wonderful. Okay, and so in some sense it's, that's its tangent line. And if f double prime is positive, what's happening emotionally with the graph of f? Okay, yes, it's concave up. That's mathematically, emotionally, what does that mean? It's smiling, yes. Yeah, there we go. So the graph is smiling, and we've got a flat tangent. What can we say about that point that I just colored in? Yeah, it's a minimum. Okay, then f has a relative minimum. All right, and in the same way, okay, it's going to be the same idea, right? F prime is equal to 0, so that means it's flat. F double prime is negative, which means its attitude is pretty negative, it's frowning. That means that f is going to have a relative maximum. That's the second derivative test. Okay? if we see that the first derivative is 0 and the second derivative is non-zero, that means that there is a relative extremum. And the sign of the second derivative can tell you what type of extremum we have. And honestly, I would like to see y'all just draw that picture every time you run the second derivative test, right? Second derivative is positive, first derivative is 0, that's a relative minimum. Something like that. Rather than just trying to memorize second derivative negative, first derivative 0 means a minimum, or is a maximum. You know, like that will fade with time. But the ability to draw a horizontal tangent in a smiling graph, that'll last with you much longer. All right, so here's an example of a problem that we can do right now using the second derivative test. Okay? There will be more types of problems that we can do using the second derivative test as the year goes on. Right now, this is pretty much it, or the most useful way, right? We've got a table of values. Find the locations of the relative extrema of y of x. One thing I'm going to let y'all try that, or at least think to yourself, okay, I see here's going to be a relative minimum, here's going to be a relative maximum. And pretty much what I was going to say, what was I going to say? Oh, y'all do this yourselves. If you're watching at home, pause the video because the answer is just going to come up in like 5 seconds. All right, there you go. So I'm over here, I'm looking at the table, and I'm looking for a place where the first derivative is 0 and the second derivative is non-zero. I found 2 of them. Okay, it's looking like, okay, I find the locations. Well, I could do a little better than that. I could say a relative minimum at -3, 5, and a relative maximum at 10, -6. Okay. And that's how we're going to do second derivative problems for now. All right, here we have just a random point of inflection question. Okay, where does the graph of f have a point of inflection? We're given the graph of f prime. Okay, so we're going to flip all the way back to the very first slide. All right, so if we're given the graph of the first derivative, we're looking for a direction change in f prime. So let's go back and look for a direction. All right, it looks like we have a direction change right here, which is x equals 2. Okay, so the graph of f has a point of inflection at x equals 2. Yes, 105, you were right. Okay, that was a nice quick example. Right. Next, we could ask you like kind of a similar question. Where is the graph of f increasing and concave down? Well, increasing, y'all are already experts on that. Okay? And you just kind of like shade on your graph, where is the graph of f increasing? Okay. I shaded it in green. And concave down, well, remember that in terms of the derivative, concave down is where the derivative is decreasing. Okay, so I'm going to kind of like off to the side so I don't color over it. Color where this thing is decreasing. So if we're asking where it's increasing and concave down, we need both the colors, yes. So that's 2 to 4. Okay. So, 2 is less than x is less than 4. Remember that and means the intersection. So where are these two things intersecting? Where we have both green and pink. All right, here, we are finally going to use our calculator in this class. Okay, now first, let's actually do this derivative by hand. This should be pretty easy. The derivative of 1 minus sine of 5x is going to be 0 minus cosine of 5x, then multiply by the derivative of the inside for the chain rule. So this should be negative cosine of 5 pi over 3 multiplied by 5. Okay, so I'm seeing that as cosine of 5 pi over 3 is a half. There's just a little bit over. Multiply by 5, that's 5 halves, make that negative 5 over 2. Okay, but we want to be able to do this using the calculator. So I'm going to bring in the calculator. Okay, so there it is. So what we're going to do is we're going to use Math 8. Use a different color. Yeah, and for most of you, if you're using, one of the newer TI-84s, Math 8 is very intuitive. I'll show you what it looks like on the new ones over here. We click Math, we click 8. Now we need to be in radian mode at all times in this course. Okay, I know physicists are going to have a hard time needing to switch back and forth. Okay, we're going to take the derivative with respect to x of, we're going to type in the function 1 minus sine 5x at the point where x is equal to pi divided by 3. And then look at that. Negative 2.4999. We round to 3 decimals in this course. So that's negative 2.500. Okay, you can also truncate. You can call that negative 2.499 with no penalty. Does anybody in here use a TI-83? Or when you press Math 8, not get something that looked like that? Anybody saying end deriv? Okay. You? Yeah, okay, good. That's how I learned how to take the derivative on the calculator. If you have end deriv, what you're going to do, the syntax is you're going to type in the function. You're going to use a comma, which I'll just show you for those of you watching at home, is right here, right above the 7. Okay, f of x, comma. You're going to type in x, so it knows to take the derivative with respect to x. And then you're going to put in, the value of x that you want to take the derivative. So in our example, I would, type in, okay, it'd be end deriv. I would put in 1 minus the sine of 5x. I would put a comma. I would put an x. And then I would put, a pi divided by 3. And then you would get the exact same thing. That's the syntax if you don't have the nice TI-84 new software. All right. Well, I should probably get that calculator out of there. But we're going to do a little bit more straight line motion problems. We're going to talk about speed, speeding up, slowing down, stuff like that. So the definition, speed is the absolute value of velocity. Okay. So speeding up really means like you're getting faster, right? Your speed is increasing. As in, the absolute value of v is increasing. Okay, so if we have a graph of v, absolute value of v increasing could look like this, right? Positive and getting more positive. But it could also look like this. It could be negative and getting more negative. And in the same way, slowing down means speed decreasing. Okay, or the absolute value of v decreasing. Well, if the absolute value of something is decreasing, that means it's getting closer to 0. So we're getting closer to 0. But it could also be like that. Now, what you're going to remember about speeding up and slowing down is that speeding up is that velocity and acceleration have the same sign. And for slowing down, what you're going to remember is that v and a have opposite signs. All right, so let's do a quick example before I end this video. All right, here we have an example from a recent AP exam. It was 2016 AB2. Okay, so you're allowed a calculator on this. Okay, they say we got a particle moving along the x-axis. Velocity is given. Okay, well, I'm going to bring in the calculator. There it is. Okay, I probably need to shrink the question so it's still visible. All right, there we are. And we're just only going to do part A, but we would know how to do part B as well, right? Because we know change in direction means, a sign change in V. So what we're going to do is we're going to plug V into Y1. Okay, I did that. 1 plus 2 sine of x squared divided by 2. And then what I'm going to do, if I'm analyzing speeding up versus slowing down, I need to check the signs of V and A. Okay, so I'm going to say for part A, V of 4 is, I'm going to find that out using the calculator, and then a of 4 is something else. Okay, so v of 4, I'll find by just calling on y1, like f of 4. So I'm going to go over here. Y1 is in variables. You just click over to y variables. We're in function mode, so we want function y1, because I plugged the equation for v into y1. Okay, so y1 of 4. Okay, I actually didn't know that the calculator was willing to do this until somewhat recently, only a couple of years ago, and it's really nice. It knows what you mean. It's like f of 4, or v of 4 in this case. Okay, and that's 2.979. Remember, always 3 decimals. All right, and then I'm going to find a of 4 by finding the derivative of b at x equals 4, or at t equals 4. So I'm going to use math 8. Derivative with respect to x of y1. And I'm going to get my y1, because I'm taking the derivative of y1. So I'd find my mouse. Y1 at the point where x is equal to 4. Okay, you don't have to use the t. Okay, and that's negative 1.164. So, what you would say to justify your answer is, since v is positive and a is negative, the particle is slowing down. Because its speed is decreasing. Okay? And that's all I got for you for this video.